సార్ అది bsh1 అది ఎవరు ఉపయోగించొద్దని చెప్పండి. విజ్ఞాన్ bsh1. అది ఎవరు ఉపయోగించొద్దండి. మీరు మధ్యలో ఓకే. ఒకసారి చెప్పండి మళ్ళీ ఏదైనా మారుతారా? ఓకే సార్, థ్యాంక్స్. మీరు కూడా ఆర్డర్ వేరే దాంతో రండి, దాంతో రావాలి. హలో. వాట్సాప్ చేయనా, మెయిల్ చేయనా? ఓకే సార్, ఇది ఈ నెంబర్. మీ పేరేంటి సార్? కృష్ణ. ఓకే సార్, నేను పెడతాను. వన్ సైడే. అంతే, రెండు కూడా వన్ సైడ్ వచ్చింది. ఏ4 కాదు. మేము తీసిన లాగానే యాక్సీజ్గా 400 కాపీస్. నేను చేస్తాను. సార్ ఉంది ఏదేంది ఎవరో అందరూ చెప్పాము మరి ఎవరితో అసలు చైర్మన్ సార్ లేరు మరి ఆయన వైజాగ్లో ఉన్నారు ఏమని చెప్పలేను ఎందుకంటే ఇక్కడ సైమల్టేనియస్ జరుగుతున్నాయి ఎవరో ఇస్తే వాళ్ళు ఆ టైంకి ఒకసారి చెప్తాము బీసీ గారికి కూడా నేను వెళ్ళి ఇన్వైట్ చేశాను అందరినీ పర్సనల్గా ఓకే ముందు స్టార్టింగ్ ఎవరు చేయమంటారు చెప్పండి అదే అదే అంటే ముందు స్టార్టింగ్ మీరు తీసుకుంటారా నన్ను తీసుకోమంటారా నేను అంటే మీరే మొదలు పెట్టినట్టయితే మీరే మొదలు పెట్టంటే మొదలు పెట్టేసేసి గెస్ట్ని ఎవరంటే డీల్ చేస్తారు మరి స్పీకర్ని స్పీకర్ గురించి మీరు చెప్తారా అది మీరు చెప్పారు మీరు సరే అయితే వై నాయుడు గురించి మీరు చెప్తారా ఎవరో ఆయన గురించి కూడా చెప్పాలి కదా రెండా అదేలే స్పీకర్స్ వచ్చారు కాబట్టి వస్తుంటారు కాబట్టి వాళ్ళందరూ చెప్పాలి కదా ఎందుకు ఎన్ని వాళ్ళని ఇంట్రడ్యూస్ చేశారంటే మీరు చెప్తే బాగుంటుంది నాయుడు గురించి ఓకే 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 అయితే మరి పెట్టామని మెసేజ్ మరి ఏమంటున్నావుతో తెలియదు మరి ఉంటే మనకి పర్సనల్ కలవచ్చు కానీ మరి ఫోన్లో మనం కలవలేము కదా ఆయన వైజాగ్ ఉన్నారు మళ్ళీ బీసీ ఒకసారి ఫోన్ చేస్తాను 2:30 అప్పుడు చెప్తాను రమ్మని మా హెచ్ఓడి గారు ఉంటారు వస్తే ఆయన కూడా మాట్లాడమని చెబుతాను నేను చెప్తాను ఏముందా వచ్చారని ఆయన కూడా వస్తేనేమో ఆయన కూడా ఇవ్వండి ఒక ఛాన్స్ అయితే మిగతా ఎవరు రాకపోతుంది నాకు తెలిసి ఓకే పర్లేదు ఓకే అది ఆర్డర్ పర్లేదు ఏదైనా పర్లేదు ఓకే అదే యాక్చువల్లీ 100 మంది ఉంటుంది లిమిట్ మళ్ళీ యూట్యూబ్ లైవ్ కూడా పెట్టాను అది కూడా పంపిస్తాను మీకు లింక్ ఓకే పర్లేదు లిమిట్ అని మీరైతే వచ్చింది మెయిల్ వచ్చింది ఓకే మా వాళ్ళకి కూడా నేను మెయిల్ పెట్టాను అందరికి మా ఫ్యాకల్టీ అందరికి మరి మ్యాక్సిమం ఎక్కువ మంది రారు వాళ్ళు ఎందుకంటే ఈ సైమల్టేనియస్ చాలా దొరుకుతున్నాయి కాన్ఫరెన్స్ దొరుకుతుంది ఏదో స్కిల్ డెవలప్మెంట్ దొరుకుతుంది అని బయట తీసాను ఏంటి మీరు క్లోజింగ్ ఏముంటది ఇంకా అవార్డు చెప్పాల్సిన అవసరం లేదు కదా మీ మూమెంట్ అనేది ఏం చెప్పాల్సిన అవసరం లేదు అదే మీరు పెట్టాయి కదా నేను టైప్ ఇచ్చాను చూపించాలా వీడియోలో ఓకే పార్సిల్ టు హిమ్ చేసింది నేను నిన్న వస్తానంటే మళ్ళీ ఈరోజు నేను రాలేను సార్ అంటే మెసేజ్ పెట్టింది నేను రాలేను మీరు పార్సిల్ చేయండి అన్నది ఎందుకంటే 4 o'clock కూడా వస్తే ఎవరితో వాళ్ళ పిలిపిస్తాను మేడం మీకు రేపు న్యూస్ పేపర్లో పబ్లిష్ చేస్తానని చెప్పాను కూడా ఇది ఒకసారి మాట్లాడండి 4 అప్పుడు వచ్చినట్టు వెళ్ళిపోద్ది మాకు 3 to 4 చెప్తున్నా అంటే మనం వెళ్ళి మన రేపు ఎవరైనా ప్రెసిడెంట్కి గ్యాండ్ ఇస్తాం మన ఇచ్చే బదులు ఉంటే బెటర్ కదా సరే అంటే నేను అన్ని మీకు లింకులు పెడతాను లింకులు యూట్యూబ్ లింకులు అది దానికి సరిపోవడం యూట్యూబ్లోనే అటెండ్ కావచ్చు పర్లేదు తర్వాత ఇంకేముంటది ఇంకా ఓన్లీ వీఆర్ గోయింగ్ డిస్ట్రిబ్యూట్ అని ప్రెసిడెంట్ గారు ఉంటారా అంటే ఇంకేముంటది ప్రాబ్లం ఏంటంటే మళ్ళీ ఆయన అవార్డు తర్వాత ఏమన్నా అవార్డు ఇస్తారు మీరు ఇదేనంగా లెటర్ ఇస్తారు మీరు ఓకే 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 సరే this moment unfortunately we are not able to give to him personally maybe we are going to send him parcel. courier to the USA. Sure, no problem. Okay. Okay. Thank you. Hello. Okay, madam. Okay, sir. One second, sir. Just yeah, sir. Okay. Yeah. Yeah, same thing, sir. I'll send you the link, sir. Sure, sir. This number has a WhatsApp, sir. I will send to WhatsApp. Is it okay? Sure, sir. No problem, sir. Can you put the message to this number, sir? Message, your email and message. I will send you. Okay, sir. Thank you. నేను మార్చలేదు సార్. మొన్న ఏదో వేరే వాళ్ళు మార్చారట్టుంది. అది ఒకసారి మార్చితే ఆటోమేటిక్‌గా అదే మారిపోయింది. ఇంతకుముందు ప్రీవియస్ మీటింగ్స్ కూడా. ఆ మళ్ళీ ఒకసారి మెయిల్ పెట్టండి కెమిస్ట్రీ అని. సేమ్ ఐడి పాస్వర్డ్. అది మొన్న పెట్టారుగా మెయిల్‌కి రిప్లై నేను పెట్టనా లేకపోతే? మొన్న మీరు మెయిల్ పెట్టారు కదా! మీరు ఎంతమందికి పంపించారు? వాళ్ళందరూ వస్తారండి సార్? అదే మీరు లింక్ ఇప్పుడు ఆల్రెడీ 20 మినిట్స్ ఉంది కదా! ఎవరు పంపించారో చూసి ఒకసారి నేను లింక్ పెట్టేసాను డైరెక్ట్‌గా. అదైతే డైరెక్ట్‌గా వచ్చేస్తుంది. పెట్టారు లింక్ మీకు పెట్టే చూడండి లింక్. అది జస్ట్ ఆ లింక్ క్లిక్ చేస్తే ఆటోమేటిక్‌గా వచ్చేస్తుంది. మిగతా ఏం చేయాల్సిన అవసరం లేదు. లేదు సార్. అది ఏ ప్రాబ్లమ్ అయిందంటే ఇది వేరే మధ్యలో ఎవరో మార్చారు అది. ఓకే. నేను ఆల్రెడీ పెట్టేసాను లింక్.
అయ్యింది ఇది బాగా ఉంది. నా ఛార్జింగ్ ఉండద్దు. హలో సార్ ప్రభాకర్ గారు. హలో ఎక్కడ
సార్ గుడ్ ఈవినింగ్ సార్. No, sir. Actually, I just put it again. Just can you check it? I think only password little bit change. The chemistry, the ID is same. 948-356-1516. Password is chemistry. I sent you to your mobile, sir. The link can forward to your friends, sir. Oh no, sir. Chemistry. Just last week, 2 days back, they have changed for some reason. Chemistry, sir. Chemistry. All are small letters. HEMEMISTRY. I sent you your mobile, sir. Just now. Hello. Hello. ఇది నాసా అని ఫిగర్ అందుకనే సార్. ఏదో నాసా బొమ్మ ఉంది అదేనా? ఓకే సార్, నాసా బొమ్మ ఉంది, మీరు కింద ఉన్నారు, నేను పెడతాను సార్, లింక్ పెడతాను మీకు. థ్యాంక్ యూ సార్. ఓకే సార్.
Hello. Reaction chat.
Hello.
Yeah, hello.
Sir, good afternoon, sir. Sorry for inconvenience for changing that password. I think in between by mistake
Yeah,
somebody
it is
changed.
yes. Okay, now it has gone Zoom again. What happened? Yeah, it went. How do I now? How do I
Go to,
get
sir.
my?
So maybe go to, actually I need to make you host, sir, for that.
Okay.
Then you can go to the share screen. Below you have a green color one, bottom. You have green color one, share screen.
Which one? Oh, share the screen.
Yeah. So
Okay.
there, that you have to open your PPT and just go to the share screen. Whatever on your piece you are going to present, that same thing will appear, sir.
Okay. Now I want to upload the presentation. How do I do that?
Okay, sir. I'll make you the host, sir.
In fact, my daughter taught me yesterday just to bring the file.
No problem, sir. No problem, sir. Now I make you host, sir. So
Okay.
maybe now you go to you first open your PPT, sir, on your laptop.
Yeah. So on this screen, do I have to open something else?
On your laptop, you open not that screen, sir. Laptop, open your PPT.
Yeah, my laptop is open. Oh, you want me to open the file? The presentation.
Then you go to the share screen, sir.
Okay, now its presentation is opening.
Okay, then I go to the Zoom share screen.
Now did this open on the Zoom? No.
In Zoom, you go to the below. You have a green color share screen button, sir. Below of the Zoom app.
For that share, you want
Yeah,
me to type?
share screen.
Yeah,
A green color one.
What happened to this? Okay, now share. Okay. Now I'm sharing this thing. So I just open my file.
Okay, sir.
Socket API. Okay. Please bear me.
Sure, sir.
Because
No problem, sir.
forensic computer guys does everything. So
For most of us, it's first time, sir. So that's why we also such kind of mistake, small password mistake has happened.
okay, now I've opened the screen. Are you able to see this?
1 second, sir. Says not responding. Maybe internet slow. So 1 second.
I am able to see Andy.
So you are able to see the presentation?
Yes.
Okay. Yeah, that's so everybody should be able to see now. You are sharing a screen. Oh, I see. Okay. Hi, Yashodhara. It seems somebody changed the password now. The password is chemistry, all small letters. Fine. So yeah, I have already logged in, and I just want to. I mean, they're helping me. I mean, I can see I downloaded the thing, and so that is basically where we are. Okay. Why can't you join for a minute and then afterwards you can go? Will that be okay? Okay. All right. Chemistry. Pass code is chemistry. All small letters. Bye. Okay. Hello. Oh, Devaki. Put your sound on. Let me introduce to Dr. Basveshwar Rao. Here, he is a professor, Basveshwar Rao. Hello, sir. How are you?
Hello, I'm good. How are you?
Yeah, let me introduce Dr. Devaki Nandan. He's on the top. You guys will say both hello each other, Devaki.
Hello, sir.
Hello, hello. Namaste.
Yeah. So he's the one I have sent the details to you. And then he, okay. Yeah, I just wanted.
Our president will join soon, within 5 minutes.
Sure.
It is not 3 yet. So another 3-4 minutes time is there.
No, that's fine. I just wanted to practice it. In fact, we were trying with that Naidamma. Now I have to send our MSc chemistry batch is next year coming. We are going to meet 50th reunion. So I sent those guys actually in Ayodhama. Now I have to send them as if it is chemistry. And we got another gentleman, Dr. Balram. Hello, sir. How are you?
I'm fine, sir. I don't know whether I'm audible or not. 1 minute.
Yeah.
Yeah, I'm fine, sir.
Yeah. Okay.
Are you
Good.
able to see me?
Sorry, say that again.
Are you able to see me?
Yeah. Yeah. Sure. I'm seeing you. Yeah. Yeah. I saw
Yeah.
it. Yeah.
How
Yeah,
are
it
you,
still
sir? I
says.
look forward to your wonderful lecture.
Oh, you're welcome. My only problem is you guys have to speak a little bit loud
Fast.
because I'm short of hearing. And well, age brings these sort of things. And also what we do in the life, it will hunt you back at the later stage of your life. So that is.
How are you, Basveswara Garu?
Sir, namaste. I am fine, sir.
Nice to see you.
Oh, I see. Raise the hand. That's where it is. Okay. I was looking. Where is he raising his hand? So, they okay. You want
Yes, sir.
to? Yeah. Why can't you just get in? You should not be shy. See, the reason I asked you is you should know these people. Dr. Basveswara, he looks humble and quiet, but he's very, very well knowledgeable. That's where I feel.
It's really a great pleasure to meet all these people. Really nice, and thank you for introducing me to Dr. Basveswara Garu. And I'm seeing all stalwarts on the screen. Balram Garu and other people who will be joining.
వచ్చారా సార్?
హలో
సార్ నేను బసవేశ్వరరావు.
సార్ ఇంకా పేషెంట్ ని చూస్తున్నాను సార్ నేను.
అంటే మరి
చూస్తున్నాను.
టైం పడుతుందా సార్?
మీరు స్టార్ట్ చేసేయండి సార్. మీరు స్టార్ట్ చేసేయండి.
అంటే మీరు ఒక 2 వర్డ్స్ చెప్పి.
ఉన్నాను సార్ నేను వార్డులో ఉన్నాను.
ఓకే సార్.
వార్డ్ రౌండ్స్ లో ఉన్నాను సార్ నేను.
ఓకే సార్. ప్రభాకర్ రావు.
ఓకే, ఆయన పోస్ట్ చేశారు.
Was here a minute ago. I think he's.
డాక్టర్ కోరియా ప్రభాకర్ రావు.
Balram Garu.
Namaste, sir. Cheppandi.
I had a lot of friends from NGO. I studied at Dhanbad, Indian School of Mines.
ISM Dhanbad. Yeah, I visited a couple of times there.
I used to have a lot of friends there.
Yeah.
A very good friend, actually, he retired. BNP Agarwal.
Yeah, BNP Agarwal. Yeah.
Agarwal.
In fact, we had a lot of people from ISM Dhanbad.
Yeah, that's right. That's how. And another, actually, there used to be Professor Verma. I mean, maybe he's passed away. He's very much older. Jay Singh.
Yeah, Verma, a couple of Vermas were there, yes. But SK Verma is still.
Yeah, SK Verma is still there. Yeah. We used to call him Popatal. I mean, I shouldn't say that. He's from BHU. He did geophysics from BHU. His name is Srivastava or something. It's a short guy and chubby guy.
Yeah.
He went to South.
I'm also becoming old. Keep forgetting.
No, I didn't. I mean, I'm already old. It's not the question of that. But this particular guy, also, I'm sure, he went to even at Southport. Indian have a center there, right? A station, experimental station.
In Antarctica, yeah.
He went there. The moment you said NGRI, it all brings the. It all brings the memories of. I mean, I was at Indian School of Mines in '74.
Okay.
75 left India to England.
Okay. You are right now in America, right?
I'm in US, yes. I'm in Washington, DC.
Near DC, which place?
We are actually in a place called Bethesda, Maryland. Bethesda is outside.
Okay, it's part of Maryland. Okay.
Yeah, I mean, actually.
My son lives in Brambleton.
Which one?
Brambleton. Earlier, he used to live in Herndon. And now he
Herndon. Actually, the gentleman who is on the top, Dr. Devaki Nandan Chebolu, he lives near that area. So he is familiar more of Herndon.
I was about to tell Brambleton is very near to me. I live in Ashburn.
Ashburn, yeah. Ashburn is...
He live maybe 10 minutes, 15 minutes to our house. Brambleton is very near.
Yeah, last October, up to September, we were there at Ashburn, Brambleton.
Oh.
A nice place.
Yeah.
Nice
very
place.
well planned.
Yeah. Close by to the airport. For everything, I think it's quite nice. So, since you said you went to England, and how long you were there? Where you were there? Sir, you Apparagar, you said you went to England from Dhanbad.
Oh yeah. I actually went to work near Oxford. Then I got my degree from Liverpool. I worked for the British UK Atomic Energy.
Oh.
So there is a place called Harwell, and United Kingdom Atomic Energy Authority, UKAEA.
Okay.
Then afterwards,
Prabhakar Koya, are you there on the line? Mr. Prabhakar.
Yes, sir.
So shall we start? Our president is busy with some operation surgery, I think. He's still in hospital.
I think we have mentioned 3 o'clock, sir. So we'll wait 5 minutes, sir. After 5 minutes, we'll start, sir.
Only 5 minutes.
Yes, sir.
Okay. Your Vice Chancellor joined?
No, sir, not yet, sir. I'll call
Okay,
him, sir.
we'll start by 3 by any means.
Okay, sir.
Okay.
So Oxford, when you said Oxford, I visited Oxford University in 2016. I gave a talk.
I see. I'm talking. Yeah. So 2016 is, in fact, 2016 I was there in England. I went to a place called Cheshire.
Okay.
Actually, England is a second home to me. I miss England a lot.
England, London, my daughter lives in London city itself.
Oh, I see. Have you been to the British Museum?
Yes. In fact, my daughter and son-in-law, they give some software to British Museum. British Museum is their customer. They have a company called Gamer.
No, I just want to, Did you see this Amaravati?
No.
That
No,
was
I
closed
think in
actually.
2016 only I visited
In British
Amaravati.
Museum.
2016.
No, in British Museum,
Yes.
once basically it is India, Egypt, and Greece. So that's
Okay.
it. And in the India exhibits, it is the Amaravati Stupa.
Okay.
Unfortunately, we don't have.
I think I have seen it. My daughter and son-in-law, they took me to several important rooms there. Halls, we call. They halls, yeah.
Okay, he wants to.
Nice talking to you, sir. I think we are going to commence the program.
మరి చెప్తే మరి ఇక్కడ ఉన్న వాళ్ళే
సార్ ఇదేగా ముందు
జూమ్ లింక్ దాన్ని క్లిక్ చేసి
ఇదేగా ఓపెన్ చేస్తాను కరోజన్ ప్రోడక్ట్ ఇదేగా
ఏదో ఒకటి.
ఓకే ఓకే
హలో
మేడం
చెప్పండి.
హలో చెప్పండి మేడం, మీరు స్టార్ట్ చేద్దాం.
హలో
సార్ పేరు అప్పా జోస్ల శ్రీనివాసరావు గారు.
ఓకే ఓకే.
మీరు టూ వర్డ్స్ చెప్పారు.
అయిపోయిందా
హలో
ఫస్ట్ మీరు టూ వర్డ్స్ చెప్పండి మేడం. వెల్కమ్ మీరు చెప్పండి మేడం.
ఓహో ఇప్పుడు దీనికి వస్తాను ఆయన లేదు నాది అయిపోయింది. నాది ఇది మన క్లాస్ది కెమిస్ట్రీ ఉంటుందమ్మా. ఈసీ సెషన్ 3 ఆన్ చేసే కెమిస్ట్రీ
చెప్పండి.
ఇచ్చారా? నేను ఆల్రెడీ సునీత ఓపెన్ చేసింది. సరే ఇక్కడ చూసుకోవా నోటీస్ బోర్డు మీద విబిటి 8 అని ఉంటుంది. సెక్షన్ 11 ఇక్కడ ఉంటుంది. లేట్ సెక్షన్స్ కమ్మా.
మీకు ఎప్పటి నుంచి ఎగ్జామ్స్
ఒక్క నిమిషం ఇక్కడ విబిటి 8 11 కింద సునీత మేడం
ఓకే.
మొత్తం మీదకి అయితే ఎగ్జామ్స్ రాస్తే కానీ పాస్ చేయలేదు అయితే పెట్టేస్తున్నారా?
హలో, గుడ్ ఈవినింగ్ సార్. గుడ్ ఈవినింగ్ ఆల్ ఆఫ్ యూ.
Hello, our honorable Vice President Professor Sarojamma garu will invite the guest.
Good evening all of you. Today we are very happy to invite Dr. Appa Josila Rao garu to deliver the lecture Mechanism of Corrosion Product Growth on Nickel Aluminum Bronze Ammonia Seawater Interface. Sir, we are very happy to invite you to this occasion, and we are very happy that during this period we are able to arrange this lecture. Thanks to our Secretary Baswesar Rao garu for making this lecture to be possible on this occasion, and I request you, sir, to deliver your lecture. Our president will join very shortly. Now I request you to deliver the lecture, sir.
Honorable today's speaker Srinivasarao garu and Vignan University Administration and our honorable Executive Council members of Andhra Pradesh Academy of Sciences. On behalf of Andhra Pradesh Academy of Sciences, I invite all the participants. I would like to throw some light on Yalavatti Naidamma, who is a scientist, basically chemical engineer, is born in 1922 and unfortunately he passed away in 1985 on some unfortunate attack, bomber attack on Air India flight. So Professor Naidamma is a famous scientist who hails from Tenali, a Guntur district of Andhra Pradesh. He served as Director General of Council of Scientific and Industrial Research. He also served Central Leather Research Institute and also 4th Vice Chancellor of Jawaharlal Nehru University, New Delhi. And is basing on his credentials, Andhra Pradesh Academy of Sciences established an endowment lecture which will be given by famous scientists every year. Every year one scientist delivers endowment lecture. This year we are fortunate to have Dr. Appajosula Srinivasarao Garu, and on behalf of Andhra Pradesh Academy of Sciences, we thank all the participants for attending this program. Now I request Professor Koya Prabhakar Rao to introduce our today's speaker, Dr. Appajosula Srinivasarao Garu. Koya, kindly introduce.
Thank you, sir. Actually, I think the host I make, the host is Appajosula Srinivasarao Garu. You can mute all of them, sir. Otherwise, you can make me to host again back so that I can mute all of them. This disturbance will not be there, sir. Sir, Srinivas Garu, are you there? Hello.
Koya, kindly mute everybody except the speaker.
No, sir. Actually, I make him host, sir. If the host is there, then I cannot make, sir. That is the reason why.
Okay. I request all the participants kindly mute your. Kindly mute, otherwise unnecessary disturbance is there.
So you click on your mic near to the video.
Dr. Rao, can you please mute everybody? There's an option for you to mute everyone. Can you please go ahead and mute all? Dr. Rao, there is an option for you to mute everyone. Can you please go ahead and mute everyone?
Yeah, we are doing it.
Actually,
Koya, kindly mute it.
Yeah. Srinivas Garu is there? Srinivas Rao?
Yes.
Sir, can you make me host, sir? Because I made you host. That's the reason I'm not able to mute. Otherwise, you can mute, sir, all of them. There is an option, mute all of you, all of them.
He's instructing you to mute everyone. You are the host of this Zoom call, so you have the ability to mute everybody. So please go ahead and click on the participants on the right-hand side of your screen. You should see participants. When you see participants, you will see a microphone symbol. If you can go ahead and mute them. Dr. Rao?
Yeah, I'm seeing.
Yeah, I'm trying to instruct him I'm trying to help him.
Yeah, kindly.
Nana. Andari mute cheyal, Nana. You're muted. Go ahead and unmute yourself so we can walk you through this.
Yeah.
Karnam Ramkumar Garu, please mute yourself.
Okay. Right-hand side is participants. Click on participants.
Where is the participant?
Yeah,
I can't
now
see.
Everybody Garu, please mute yourself, sir.
Why can't you, Prabhakar Rao, why can't you mute all, because I'm not able to do that.
Because your host, sir, you can mute because that account automatically lost because I make you as a host.
Can you make him host? You are the host of this conversation. That's why it's not allowing it. So you have to give him permission.
You have to give me back me, sir, that host things. Then automatically I can mute all of them.
Okay, go ahead and mute yourself.
This is me. You are talking to me.
Yes, sir.
Yeah. Please go ahead and mute yourself and I will call you so I can walk you through the steps.
Okay, okay, madam. Good afternoon to one and all. First of all, I am very much thankful to Andhra Pradesh Academy of Sciences for giving me the opportunity to organize this Y. Naiduma Endowment Lecture Award talk. I am also thanking to our management for giving me the opportunity to conduct this. First time, I think we are conducting such kind of endowment lecture from our Vignan University. I must thank our management also. It gives me immense pleasure to introduce Dr. Appajula Srinivasarao Garu, who is a wonderful scientist from his contribution is there all over the world. Dr. Appajula Srinivasarao hails from Nidupurolu, local of Guntur district. He attended ZP High School and PB College, Nidupurolu. He received MSc Physical Chemistry from Sri Venkateswara University, PhD Applied Chemistry from Indian School of Mines, and also he has another PhD from Metallurgy and Material Engineering from the University of Liverpool, England. He also received MS degree from Engineering Management from George Washington University in USA. Dr. Rao currently works as a program manager of the Office of Research, US Nuclear Regulatory Commission, US NRC. Prior to joining US NRC, he worked as a senior scientist at US Naval Surface Welfare Center, professor, lecturer, and associate professor of materials engineering. Dr. Rao research expertise in the area of solid-state chemistry, colloid and surface chemistry, advanced nanomaterials synthesis and processing, deformation in materials for nuclear and non-nuclear applications, corrosion, and analytical and advanced modeling using finite element analysis. Neutral network analysis and molecular dynamic simulation also is another area of work. He published nearly 300 research papers in journals, conference proceedings, and government technical reports and publications. He presented more than 350 talks throughout the world. Dr. Rao has 5 patents disclosed to his credit, and he also received nearly 50 national and international awards and national international repute. Dr. Rao lives in Bethesda, Maryland, and he married to Padmavati. He has 2 daughters. Sharda going to her fellowship in cardio, and Yashoda finishing her PhD in materials engineering. So with this much introduction, I'm feeling pleasure to invite him to deliver his talk. Thank you, sir.
పీజీ సెంటర్ కూడా తీసేస్తారంట. ఎంఆర్ఎంఎల్ డిగ్రీ కాలేజీలో ఎయిడెడ్ కోర్సులను కూడా గవర్నమెంట్ హ్యాండ్ ఓవర్ చేసేస్తున్నారంట. చేసి కాలేజ్ వాళ్ళు తీసుకుంటారు.
Who is making that noise? Nonsense.
Hello.
ఈ అమ్మాయి
Hashita madam, please make it silent.
అమ్మేదానే కదండి.
Hashita.
అందరిదే అంటున్నాను, అందరూ పంచుకోవడానికి. మరేమో
Hello. Sir, you can remove, sir, if anybody is not silent.
Yeah. Okay, can I?
Yeah, start, sir.
Okay. Well, it is nice of you for inviting me here and give a talk.
అంటే ఇప్పుడు ట్రస్ట్ లో చైల్డ్ పర్సన్ అమ్మాయి కదా, వీళ్ళకి ఆస్తులకి రైట్ ఉండదు. ట్రస్ట్ ని గవర్నమెంట్ హ్యాండ్ ఓవర్ చేసుకున్నట్టు చేసుకుంటారు.
అప్పాజోసి శ్రీనివాసరావు గారు, మీకు ఒక పక్క పార్టిసిపెంట్స్ ఉంటది, ఎవరైతే
అలా చేస్తారు
మ్యూట్ చేయాలో వాళ్ళు మ్యూట్ చేయండి.
దీనికి ఇప్పుడు మాస్టర్స్ ట్రస్ట్ కి ఆస్తులు పంపకాలకి సంబంధం లేదు.
I only see mute myself. Okay,
అది
just
లాస్ట్ లో ఉన్నది ఏం లేదని
Sir,
చెప్పి ట్రస్ట్ హ్యాండ్ ఓవర్
one.
చేసి వస్తుంది గవర్నమెంట్.
Hello? ఎక్కడ చేయాలి చెప్పు.
చేర్చుకోవట్లేదు అశోక్ ఏంటి చాలే సీఎం వచ్చి చేర్చుకుంటాడు వచ్చి.
I'm not able to see అమ్మా.
బీజేపీలో కలుస్తారమ్మా వైఎస్ఆర్సీపీలో
It is
కలవడానికి.
only
Sir, you can make somebody co-host so they can mute others.
వాళ్ళకి అక్కర్లేదు అన్నట్టు ఉంది ఎవరోనే.
You make somebody co-host or yourself can be co-host, sir, so that you can mute others.
సపోర్ట్ చేయాలి కదా.
why can't you
వాళ్ళని హ్యాండ్ అవుట్ చేయండి.
Dr. Basveshwara,
yes, sir.
why can't you ask Prabhakar Rao, why can't you take control and
ఎందుకులే అంత ఫ్యూచర్ నేను ఆక్రమించుకున్నదాన్ని.
Srinivasrao garu, sir, Lakshmi Kumar speaking.
ఏమ్మా
Can I suggest something?
నా చేతిలోకి వస్తుంది ఇప్పుడు ఎందుకులే ఆడవాడని ఒప్పుకుంటున్నాడు.
You can make somebody co-host. You just go to their name. Probably our
okay, just my చెప్పు.
Press stop share. Press stop share.
Okay,
you go to anybody's name and the
Now you see
participant
everybody,
name.
right?
yeah,
Okay. You see that lady that says Hasita in the red sari?
okay, start this,
ఆ మూడు చుక్కలు ప్రెస్ చేయండి. అక్కడ 3 డాట్ ఆమె పైన ఇట్లా అనగానే కార్నర్ లో 3 చుక్కలు
ఇదే
ఉంటాయి. blue
ఇదే
dot. ఆహా ఆ రెడ్ సారీ.
ఓ ఇదే
Yeah, press that and it should give you an option to mute her. Something to mute.
అది మ్యూట్ పైన ఉంది.
మ్యూట్ అంటే it is mute. Okay,
Yeah, mute her. Okay. Now you see Prabhakar, go first find Professor Prabhakar.
okay,
Prabhakar and click on the మూడు చుక్కలు పైన.
okay,
పైన.
okay,
Prabhakar.
okay.
ఆయన కాదు ప్రభాకర్ దగ్గరికి వెళ్ళండి.
Oh, ఈయన ప్రభాకర్ కాదా? ఓకే, yeah, he is a Prabhakar.
ఓకే ప్రభాకర్ దగ్గర 3 చుక్కలు ప్రెస్ చేయండి.
Okay,
ప్రెస్ చేసి ఎక్కడన్నా మేక్ కో హోస్ట్ అని ఏమైనా ఉందా?
make host, yeah, I press on make
Okay.
host.
Wait. Click on make host.
Okay, okay,
ఓకే ఇప్పుడు ప్రభాకర్ గారు హోస్ట్.
okay, that's fine. So
ఓకే
he
గుడ్. ఇప్పుడు నేను జూమ్ లో నేను ఒక నిమిషము ప్రభాకర్ అంకుల్ కి చెప్తాను
okay,
దట్ షేర్ స్క్రీన్ కి మీకు పర్మిషన్ ఇవ్వమని. అది ఇవ్వగానే మీరు స్క్రీన్ షేర్ చేయడానికి ఉంటుంది.
okay,
ఓకే
okay. Dr. Prabhakar, are you able to hear? Prabhakar?
మీరు అన్మ్యూట్ చేసుకున్నారా?
Sir, kindly share the screen and go ahead.
And now Srinivasrao sir cannot share his screen because he made Prabhakar Rao as host. So co-host has to give permission.
Dr. Prabhakar, if you can kindly please select the security button.
Sir, I can now I made it multiple screens can share. You can share, sir, no problem.
Yes.
Able to share the screen. There will be an option to allow share screen. Can Dr. Prabhakar please do this?
Yes, sir, I made it, madam. I made it. You
Okay,
can share
Okay,
screen.
try to share your screen.
okay,
Press the share screen button, the green one, the same one.
okay,
Press share screen.
okay,
And then yes, go ahead and share your screen.
okay,
And you will be able to open your PowerPoint presentation.
okay. So this one.
All right.
Oh,
So
yeah.
we are set to go. We can start the presentation.
Okay, okay, now it is done. Thanks, Amma. So it's my second daughter. They know more computers than old timers like me. So now can I go ahead?
Yes, sir. You can go ahead, sir.
Thank you for a beautiful introduction. And As Prabhakar said, I hail from Dubrolo. The reason I said that one is Naidama comes 6 miles from my place. It's called Elavaru. I mean, they may call Kanali now, but he comes from Elavaru. So that was the reason. And in fact, I don't know whether it is his daughter or sister. She was my classmate in high school, in school, from my 6th grade to the SSLC. So that was another occasion for me. I've been really honored to receive this, to give you this lecture. Today, I made it quite simple. It's almost like a textbook lecture for all the people with chemistry. Most of the work, this is only about 15 to 20% of what we have done. And the thing is, we use for naval applications, seawater is a terrible thing. In fact, actually, if you have dissimilar metals in an electrolytic solution, you will have corrosion, a galvanic corrosion. So to avoid that one, we use quite a bit of sacrificial anodes and all. Nickel aluminum bronze is a wonderful material, very corrosion resistant. And here I have actually I don't know whether you guys can see, this is it's not a toy, but it is 1/5000th scale of a, well, I don't know how to tell correct what type of submarine. It's a submarine used for the naval applications for the US Navy. It was actually, we made it in the lab using single layer lithography. We designed it with the CAD CAM and single layer. The reason I'm showing only the back side is, here this is called the casing, and inside casing is actually a propeller, and that's called a propulsor. And that propeller actually, it's about, it will be about 6 feet in diameter. So you can see what happened. That is the one that propels it back. And suddenly we got one day that video, although it is very good.
Ravi, send me the link.
Hello? Can you hear?
Yes, you're audible.
Continue.
Can you guys?
Yeah.
Okay, that's fine, because I thought somebody saying that. So that's the reason we undertook this project, to get over the phone. So what we found was it is not the seawater that is corroding it. And in the submarine, all these boys will be sleeping and their washings, everything. So the soap that is used to wash their clothes, that is emitting ammonium hydroxide. And that actually flows on the backside, and it is going into the propulsor. And that's where the propulsor is being attacked by ammonia. So that's what we found. And at that time, the team that is working on, they gathered all these things for how long it takes to really crack, initiate, and all. And they got quite a bit of complex kinetic data, and they didn't know how to deconvolute or disappear the reading. So that's why they sent it to me. And so this is, with this one, I will start my, this is the basic background before my talk. I am actually legally bound to show this disclaimer that the work is done for US government, and even I'm not allowed to show in the advertisement to US Nuclear Regulatory Commission. This is only my private talk, so that's the disclaimer. I don't want to go on. So the background is, I already told, nickel aluminum bronze is used for several naval applications. The tensile stress in presence of aqueous ammonia promotes stress corrosion cracking. Corrosion is normal corrosion. Corrosion under stress, mechanical stress, is called stress corrosion cracking. So this project slightly comes into chemistry, basic chemistry, and mostly into chemical engineering and also mechanical engineering. In fact, today I'm talking only the chemistry, which is actually the first, almost like an introduction type of thing, what effort we have done later on. Because originally I thought it is I selected this topic because I is a chemical engineer. It's more of an engineering type of thing. But when Vignan host, I was told that you guys are hosting me. So it is from the basic science point of view, I made this. The stress corrosion cracking has been observed in not only at this particularly dangerous at the weld mills. Where welding is there, you have some components will be welded, and that's where it is severe. And the particular case, what is the interest for basic science is the nickel aluminum branch has a lot of elements. You have nickel, you have aluminum, you have copper, and as such, nickel aluminum branch is soft. To make it strong, they use iron aluminide. They look like a small acicular particle, and those are the strengthening agents. So we tried to do this testing by this one. Here you can see, as I said again, I gave an electron micrograph just to show these nickel aluminides, almost like a rods sticking in, and cracking and all, I forgot to remove on this slide, but that is for something else. We have seen the crack that happened on the surface. Iron aluminide is used as a strengthening agent. So our program goal is to identify the mechanism, how, what is happening, and to understand how we can mitigate it. So to mitigate some effect, we have to understand at the basic, at the atomistic level, what is happening. So that's how it came. The modeling of corrosion process is, to start with, we started with chemical reaction kinetics. Having said that one, it is not really true as what we study in chemistry, but it's chemical engineering kinetics. So it is slightly, I mean, the basics are the same, but some of the things are different. Because they're in chemical engineering, it is the surface is another additional variable parameter, which we look into that form. So in this talk, the reason I selected this one is if somebody from outside gives some talk, it will bring a new seedlings or new line of thinking for the faculty to develop their own research. It is, I mean, I have seen, it's unfortunate, I have seen in many places quite a bit of inbreeding, and then they continue and continue. There is no new thinking at all. So how do we model? What is the first step for a material to degrade? Is it oxidizes, and an oxide surface is very, very non-adherent in some cases, and some cases very adherent. And they bring the secondary sort of thing. So how do we model it? First, we follow the reactant concentration change. And how do we do that one? As the oxide is building up, you will see quite a bit of change in the weight of the material. So weight change is a process. Not only this one, there is nothing that is preventing us to follow a kinetics of a process if something is constantly changing, such as a physical property, a structure, or electrical conductivity, or something like that. The electrical property is nothing but, I mean, example is open circuit potential. You can actually see as an oxide, is building up, the conductivity goes down because an oxide is a more ceramic material. So similarly, some of the times the bare metal or bare material has one type of structural integrity, whereas the oxide that forms on the surface will have a different type of structure. So with this structural changes, you will have, if you can follow, you can see the oxide grows at the expense of metal dissolution. So that means the structure of metal decreases and whereas the oxide structure will grow. So these are all the parameters. So this is a new thought I want to bring you guys. And then here, some of the examples I will show you will tell how they match each other. I mean, so here I'm going to show the modeling of an oxide buildup. So you can see anytime you have something happening, in the beginning, the chemical reaction will be very fast. After a certain stage, it may come into steady state conditions, and eventually it may end up into saturation or slow reduction. Unfortunately, all the systems are not like that. Once it goes to some sort of saturation, it may reverse it back. That means the precipitate that is, or the dissolved substances may redeposit back on the surface and then give rise to a reversal of the progression. So we can write this chemical reaction kinetics, a simple differential equation. A rate of weight change is a functionality of the fast reaction zone, rate of fast oxide removal or oxide buildup, whatever may be the case, and then a slow. So for everything to happen, the most important thing is the diffusion. So it is a diffusion parameter also we have to take it. Simple, this one, fast oxide, slow oxide diffusion control, this we classify as type 1. And in the type 2, there could be a reverse reaction. So it is not the question of slow oxide. We can actually ignore it compared to the rate at which it is reversing. So you have an oxide buildup and the diffusion, and reverse is actually a negative functionality. So you have all those things, and I don't want to go more detail into this one because that will take, I have to do at the expense of my presenting the results. So here is a typical, in this case, oxide remover. We have taken almost this whole talk is meant to the naval applications. So we have actually atmospheric corrosion of steel used in the ships, naval ships. And then we tried, and here is a picture. The way rust is removed at T equal to 0, fully rusted. And by the time we went for about 3 hours of time, we were very successful in removal. It's very nice. And in fact, you can see the grain structure. I mean, grain in the sense, rolling direction and all those things. It is at the 180 minutes structural change. So these samples represent this curve. Stage 1, fast oxide removal. Stage 2, well, you can say it is a steady state. Stage 3, well, stage 2 is a slow reaction in this case. And then we have an overall rate of reaction. So we can actually, again, redefine the stage 1 overall rate of chemical reaction is the rate of chemical reaction. Because in the first phase, nothing is happening, continuously it is being removed. So you can remove, ignore all others. That's how you can elucidate, or you can derive, or you can make an estimate of what it is happening. In the case of stage 2, you have both fast and slow oxide buildup. So you can take an average. Well, it depends on the system. In this case, we have an average value that means 50% of the fast and 50% of the soil oxide, so giving rise to that one. But here, in the stage 2, the diffusion is 0. So this is how we made that one. But the reality is completely different to what we hypothesize. So this is the actual measured value using open circuit potential. We followed over about 40 days, 37 or 40 days, the potential change in, actually this one is in nickel aluminum bronze. And you can see a progressive growth, initial fast, and then coming into a nice saturation. And this sort of thing can be explained. So again, we can rewrite the same differential equation as the rate of potential change is a functionality of the fast potential change, and then slow potential change, and then diffusion. So this is how we can transform it. This, I am showing this one with a good intention for the next generation chemistry faculty to develop, have a new thinking in terms of anything, I mean, color change, whatever it is you can apply. The third thing is structure. In this case, we are showing the kinetics of change in the structure of nickel. Particularly the nickel, what happens? Nickel will form a nickel NiOH, and there is another formation NiOH twice. And one grows at the expense of other. So you can simply take a set of standard peaks and normalize the intensities, and you'll be able to get useful information to estimate the rate and at what it is doing. As you go into the results, you will. So the same thing again, we can write a differential equation for using the structure change as a function of a fast structure change, slow structure change, and the diffusion. So if we put this one, we can actually solve this mystery. So now coming back to our practical, what are the practical implications and how easy it is to write down these reaction kinetic equations. Some of the abbreviations, NAB means nickel aluminum bronze and all those things. And E corrosion potential, open circuit potential. Open circuit potential is the measured potential versus a standard caramel electrode. So this is the, so I was given this table and what they have measured in different cells. And so this is the equations, kinetic equations, they got it. And then they said, why can't you model it? We gave up. So I didn't know what to do. Generally, I'm a believer in normalization. So if you normalize in a model development, a lot of times there will be many variables. We start with a simple variable or simple explainable functionality, and then try to fit into the model. Then afterwards, you keep on adding some constants until we see an good agreement between the experimental, what we observe, and also model prediction. And then try to go back and explain what those constants are. If we cannot do that, then just hands off. Well, it cannot be done. So in this case, we have these things. So this is exactly the data that was given to me in the previous slide I showed you. And this is the plotted value. And in fact, this is from corrosion branch. They're the guys who got from the on-site. On-site means from the real fleet. This is the data from the real naval vessels. So when we want to model this one, first assumption I did this, we will normalize it. So normalizing means we take a reference point, generally at t equal to 0 time. So what is the history at that point? take that one as the standard, and from there it is changing. So if you divide that one, any potential at T, corresponding potential at T divided by this fixed potential T0, that will be a normalization. And the second assumption is the surface will have the same potential, and potential change due to corrosion is uniform, which is in general reality is not true. But we have to start somewhere, because if you see actually rusted steel, in fact, I'm sure everybody has rusted steel windows or something. You will see at some stage, some places it will be big lumps, some places very thin. So assuming that one is a base, it's a very, very extrapolated assumption. That is what we started with. Once we normalize it, and all those curves which have no sense at all were making some sense. What is happening is initially for about 10 to 12 days, in a lot of these samples, nothing is happening. And there is, in the literature, many different kinetic curves. There is incubation period. Some reactions start only after reaching certain goal. So this is typical of, in fact, actually, the thermal decomposition of potassium permanganate is another case. If you start heating potassium permanganate, it takes a long time. Nothing happens. And once it initiates, it's an exothermic reaction. That's a different, it actually keep on breaking and then exploding in the cell. So like that one. So in this case, for a long time, it is in constant touch. After 12 days or roughly 2 weeks, any mystery is happening. So if we can assume that the starting point for the kinetic parameter is 12 days, we got very good, meaningful results. So again, those plots we have shown here, all those things. And here you can see the first A and B. It's a funny data set of points. Maybe two different things are happening at the same time, like a stochastic process. So that is what we thought of A and B. The other things we can explain, and we created 3 types of, this is type 1, where it is a fast reaction, slow reaction, saturation. A type 2, where you have a intermediate or steady state you can call, and then a slow process. So this is the type 3. In this one, we have a fast growth. Well, I mean, because by the time I drew the lines, they look flat, but it's basically a start curve and then reversing itself. So you have fast growth, slow growth, and then fast growth again in the reverse direction. So this is how we analyzed it. And once we obtained a data set, here I'm giving an example of nickel aluminum branch. When I use the word nickel aluminum branch means without saying iron aluminate is also there. But so for simplicity, I use it as NAB. It's 80% seawater. I mean, every time, although you do many times, you will see a typo. It is a seawater and 20% ammonia solution. The reason the seawater in the sense, we had simulated seawater. Because to real seawater, the moment we change the chemistry or add something else, a lot of muck will settle down. So to avoid that one, we have the standard ASTM, American standard testing of materials. Their standard we use, and we will have that. So you have the first stage, fast reaction. So it is almost at the initial where you have aggressive type of change. Then you will have a slow change and an intermediate, or that we call it as an overall rate of reaction. So here After once we have done that one, the whole thing, the first two sets, first two, A and B, we have no solution right now. Later on, we solved the mystery of it. So if you go there, we can see. So we were seeing quite a bit of times the order at which the things are, species are changing is 0.5, which is nothing but a diffusion control. It is true, unless the solution, ammonia and seawater mixture, penetrates and see a new surface, nothing will happen. So it is, it's quite a bit. This is by open circuit potential measurement and for different ammonia concentrations. So what happens in the case of seawater, you can see a bright surface show mild corrosion. You will corrode, but it forms a plaque or maybe salt. And 90% seawater and 10% ammonia, you can see a uniform but significant tenacious corroded surface. As you go into the higher, you will see severity. When we use 50% ammonia, you can see a lot of loose, we call them a loose plaque. It comes out and it will form what's called mud cracking. And once this happens, most of the oxalates fall off. They just break down because the moment you have, and you keep on building up, it goes more into mechanical engineering or structural engineering. It builds an internal stress. When it builds an internal stress, it's a differential stress. At some layers, it will be compressive, and some layers, it will be tensile. So because of that one, they break. So this is, so the conclusion in the reaction kinetics is the overall reaction is a diffusion control. The fast oxide growth is the first order. In the beginning, nothing but the metal keep on forming an oxide. So one will expect the concentration change in 1 unit. And in the slow reaction time, it's almost like a zero order reaction. It's a time dependent. So the morphology of the oxide formed on the sample is uniform. From surface photography, that is what I have shown you before. From this one, this is the conclusion, what we have seen. So in the same way, the other set of samples. So this is, with this one, I will say how we have measured, again, open circuit potential for the second, again, we have done. What happens is that one, unlike a weight change or weight gain, some of these things, we can use our intelligence. And this is where what I tell, the difference between a technician and a scientist. A technician can do this job, but he cannot analyze it. Whereas a PhD or a PhD student must be in a position to analyze why I am doing this, what happens. So if we can extrapolate and massage the data, we can get a lot of useful information. So from the open circuit potential, which we have seen before, this sort of things, nothing. You will say order of the reaction, diffusion control, blah, blah, blah. But once we have the data, we can analyze what is actually happening at the elemental level, because it has so many things. My cat is also listening to my talk. So basically here, I will show you the weight change. I will come back to that later on. So you have a weight change, weight gain, very nice way you can do that. And again, order of the reaction. As you increase the concentration of ammonia, you will see the order changing. still maintaining its 0.5 diffusion control. And seawater is a very slow process, diffusion control. Now comes to the reason I'm just flashing these things is just to give you a perspective how to look at a problem. In doing the structural analysis, the important thing is we make some assumption to start with. We feel that the surface has a homogeneous structural composition, which is not true. But, well, we start with that one. And this change in the structure due to corrosion process is uniform, which is also scientifically, basic scientists will not agree, because there are active centers which will pose much more severity than normal situation. So with these two assumptions, we started modeling it. We followed the corrosion process over about a month and a half. And we selected from this one two basic, actually you can see between 40 and 50, you will see quite a bit of change and some new peaks are coming. This is how we have done that one and we follow. And in this case, because the other advantage we have is for analyzing different species, we followed different type of peaks. So we have iron oxide peaks, copper hydroxide, nickel hydroxide, aluminum peak, aluminum oxide peak, and that's how we have. So we normalized it. The normalized oxide hydroxide means it is the complete circulation of all these copper oxide, nickel oxide, aluminum, and so on. And this is a beautiful kinetic plot we were able to get. So this is the normalized oxide hydroxide on the surface, which came because of the chemical reaction as a function of time. And we have a fast reaction, slow, and then overall period. So we have done 2 times with 2 different reference electrodes, OCP, open circuit potential, and new means it's the second different set of open circuit potential. And weight gain measurements, weight change in the structure. Forget about the rate, because the rate depends on what is happening and all. And the importance, I will talk later on. And the order of reaction in almost all the cases is whatever may be the measurement, it is the same. So you are able to predict the functionality of a process by using whatever technique you are using it. So the structure-based analysis, in addition to the reaction kinetics, it also provides you the oxide characteristics. Which oxide is growing faster? That means you can see which element is going down. And change in the corrosion behavior of different species. There is a thing called selective corrosion. If you have copper and nickel, and you put it in some corrosive medium, let us say you put a drop of nitric acid. Copper just comes out, whereas nickel takes some time. So that is called selective leaching. So you are removing a species and in the presence of multiple components. So, and also structure-based tells the kinetic behavior of different species. So here I'm showing you an example. Oxide and hydroxide forms on the surface. Oxide in the sense copper oxide. If we have that one, you can see very nice again. For a long time, it is going to stay. Nothing is changing. Then suddenly, and then saturate. Whereas in the nickel, it takes something is happening, and which we were able to find out later on. This initial growth and comes, it forms a different oxyhydrates, different hydroxides, and that is what is happening. But once that is there, again, it is a reverse decreasing. So nickel goes down, whereas copper grows up. Same thing happens in the case of aluminum oxide. In fact, the first initial phase in all, they're called, you can say, air oxides. Once an aluminum, a thin film forms, it protects aluminum for further corrosion process. That is exactly what is happening. Then we can do this. So again, from that one, individually we are coming, normalized copper oxide on the surface. And if we assume, if we draw this one up to 15 days, or assuming the reaction is taken from 12 days, we have beautiful kinetic curve that can tell what is the rate determining step and down. Up to now, this picture looks very good, and we are able to do that. So what is the advantage of it? It comes next. But now please take cat Bhima. So here we are giving rate of reaction in almost all cases is diffusion control. Whereas in the case of iron, we found it surprisingly 1.5. And also the rate of reaction, nickel is the lowest, and the amount that is being percentage oxide formed, oxide or hydroxide formed on surface per day, copper next, aluminum, and then, so iron oxide forms at a very tenacious fashion, followed by aluminum, copper, and nickel. But aluminum is very resistant. I mean, it should not form. Then what is happening? That's where the analysis is needed. Here I'm showing the same thing, iron oxide, copper oxide, and nickel oxide, and aluminum oxide. As a function of, when I say here 0, I normalize it. That means first 12 days we remove it. What is happening is, here I have to again bring back the microstructure of nickel aluminum bronze. In this case, iron oxide, it's like a pebbles, they form, you can see the one sticking out in these things. And here one is actually dug up, and in this one picked where the pebble came out. So that left with a crater. So this is how the structure looks. So they're all identified as iron aluminide. So what is happening? I will talk about this one at the end because the functionality model, what we developed. To answer both questions, we were able to reevaluate our data. So that's the reason I stopped here, and then I'm going back. So the analysis of functionality of a model is redo and retest the model based on the results. That means, I told you in the beginning, in model development, we just should develop with simple first principles and we apply. Nothing happens, then we make keep on adding some constants or variables and then explain. So we started with this model, diffusion control. So we took diffusion control modeling, and we expect an agreement, at least close agreement between theory and the experiment. And in fact, this is the, again, when it comes, that's where the difference between general basic chemistry and chemical engineering. Chemistry, we can actually assume a 2D thinking. Most of the times we talk about gas phase chemical reactions or solution phase, everything is homogeneous. Whereas here, the difference is in a solid state. Surface plays an important role. So it is not simple 2D modeling. It's a 3D model. In 3D model, actually, if you are a theoretician or model, you can actually enjoy dreaming and imagining how things happen. You can do a lot of Monte Carlo simulation. I mean, those are the days when I did all those things. You know, what are the nearest neighbors and how it is happening and all those things. So this is a 3D, a simplistic, I don't want to give, this is my nature. I don't want to show a complicated thing and say, well, you know, finally we ignored everything. I don't want to do this one. If alpha is the volume fraction and K is a constant of kinetics and T is the time, we can see from a volumetric to the linear is 1/3 power, and then this. So here I'm showing the top are the copper oxide, which I have shown you before. And 2D model, the shape of the curve is the same, but everything is moved up. There is some sort of higher value, what is happening. So we tried several ways. And of course, let me show the other one. In the case of nickel, the reaction going up and coming down almost like a wave. Model also predicted the same thing, 3D model. All the time 3D model is much lower value. And whereas this experimental value is a very higher formation, fraction forming there. Aluminum oxide, it's a similar type of behavior. A 2D model and a 3D model. So iron oxide, again, the same sort of attitude, but it's a constant displacement. I mean, here I showed for the 2D, of course, for 3D it's quite a bit, we cannot explain it. It depends on what are the nearest neighbors and how, it's more of a simulation. And well, when we are talking about simulation things, if you have, I mean, it's not today's talk, but when we translated into stress component and doing it, we did finite element based analysis with 100 points. 100 points means we fix a net and it's that incremental thing. So if we have that one in a finite element, 100 by 100 by 100, 1 million iterations. So in a supercomputer, we just put it in next and we get the result. So that is how complex, even that one may not really satisfy. So this is the network. When it comes, that is the sort of problems we encounter. Well, maybe next year I come for engineering faculty, I may give you the talk. How it's really a wonderful thing for our structural engineers, mechanical or chemical engineering. We have done a lot of work on that simulation, and it's really very interesting to watch. So the conclusion on this one is both models show a deviation. 2D model shows similar trend, but the oxides and all oxides, they're much lower in value. Particularly for nickel, we're not able to really exactly see what is happening. A 3D model, of course, predicts much lower value. Now comes this one. If this is true, we can expedite the process by applying an external stress. Here, in this presentation, I made it very, very dilute because this stress means you have to go into finite element modeling. That is really off the record for the chemistry, basic chemistry people. So that's why whatever I can do, I just rushed out some data to show you. Normal corrosion is a material is lost. Rate of material loss is a material specific. I mean, here I'm using word metal means elemental specific, composition specific. So if you apply a stress, in normal case, it may accelerate corrosion. So in some material composition, some materials form precipitates because of the chemical reaction. Some material lose the host, some of the material is lost. So that means the host material is losing. And that gives a significant effect on the integrity of the precipitates. I mean, one example is if we have chromium, generally chromium leaves the bulk and goes to the grain boundaries. And if the environment is corrosive environment, it's simply eaten away. Again, chromium diffuses. It's all diffusion process. So that is what we are seeing. So some materials form precipitates and some precipitates may dissolve. Again, this is one typical example I will show you. I told you in the beginning, nickel aluminum in the bronze, we have iron aluminide as the strengthening agents. They come like pebbles I showed you. And under stress, they may come out. If one pebble comes out, quite a bit of aluminum, although it is very resistive corrosion, will come out along with the iron. So that is what it is. In addition to that one, the functionality for that one is adhesion and bonding of the matrix. And in fact, as I said, if we want to go into that one, we have to go again back into fracture mechanics, which is a mechanical engineering. In fact, we have done that one. In fact, the girl who helped me in arranging this meeting in her college, she did project with me, looking at the failure of aeroplane wings, sheer stress and purely a fracture mechanics problem. That is adhesion and bonding of the matrix, wing to the aeroplane. So you apply stress, you decrease the adhesion and bonding. So as a result, either precipitates or whatever it is, they come out at much faster rate and material degrades. In the case of, again, copper oxide, the rate, aluminum oxide, iron oxide was doing about 15% per day, whereas nickel was removing in 10% ammonia only 2.5%. So this is how it is. So we can say iron aluminide is dissolving or it is coming out of the sample. So once the moment it is coming, although aluminum doesn't want to come, it cannot do anything. It's all bulk. It's simply they are coming when you. So if that is the case, when you apply an external stress, it should increase. So here is one typical case. We applied about 45 KSA. And then you can see something almost like a walnut coming out of itself. And here there is another one, iron aluminum. So this is where I showed again back. There the context is different. Here I'm showing the reason for that one. So how do we do that one? We devised a unit because it should not be a big, I mean, for structural mechanics tests, we have standard rigs and all. So, but whereas here, we wanted control to small sample, nickel, aluminum, bronze, to find out what is actually happening. So if you apply a load, you will have stress distribution. And for that one, a neutral axis. And while bottom is in tension, the top layer is in compression. So you have, when you have this material losing, it depends on what forces we are looking at. So this is an exaggerated picture. In the original, iron aluminide is distributed in nickel aluminum bronze like that, let us assume, like a pebble. You apply a load. In the beginning, this is fine, nothing happens. As the material is dissolved close to at the interface of the distributed iron aluminide and the matrix, nickel aluminum bronze, it loosens the adhesional strength, and then immediately a crack initiates and then they pop off. So if they pop off, you will see a dramatic change in the weight loss because it's not a small amount that is coming off. So in fact, there are two weights, top And what is happening on the bottom? Let us assume you reverse the picture. So they pop. That is exactly what it is. So under no stress, a typical curve may look like that one. Wait. Under no stress, weight change will be, let us assume hypothetical. Under stress, it has to increase. In this case, it is much more aggressive than the top. Whereas here, it simply gravity pulls it out the moment it is weak. So this is the apparatus we have devised it. And this is the stress applicator. And then everything has to be non-corrosive because the medium inside is corrosive medium. So we have to make out of Teflon. And we made this whole thing, and this is the sample. And the solution has to be immersed way above the sample, and then we apply it. And when we apply it, here the blue is without any external stress, the reaction time in days and weight change. Whereas the purple is 7.5 kilos pounds per square inch. And whereas this one, 15 KSI. I mean, in America, we still use the old system, not the French, everybody uses it. And so that's how it is. So if we take the specific oxide, nickel in aluminum, overall oxide, the overall removal or oxide growth, or whatever you call it, is almost the same, except few data points in the beginning of 15K. But if we take individually the iron oxide, you can see a dramatic difference as we apply. It is quite a bit of jump, the rate at which it is being removed. So this is what is happening. And in fact, again, I'm showing it just to reiterate my point. So the chunks are coming out, and that is what it is. Here, again, the data points for in 10% ammonia, 90% seawater. Oh, I forgot to add that from seawater. Iron oxide, it goes with applied stress. Whereas nickel, almost iron oxides. But all oxides, we can see the trend. I don't know why some points are down. We can't explain. But I don't want to do any fudging. Just we got it, what we had. So there is an agreement between theory and experiment I showed you. Reaction kinetic behavior, the trends are similar. Absolute value is a constant shift. That means it is telling something that we misread parameter. Because if it is a random wave, then we can't. But if it is a constant shift in the curve experiment to the theory, so theory is missing something. So the only other option we had is, we never thought that there is an air oxide. Air oxide means the material is left. We don't know when it came. We had it and we cut pieces and we did. Generally, instantaneously, the material gets oxidized because of the atmospheric oxidation. So maybe that's what it is. We don't know. So we investigated it, and as received sample has the oxide. You can see that one. The top is epoxy mounted, so don't worry about it. In the next slide also you will see. But this is the air oxide. It's a very mushy type of oxide around the surface. Whereas here, after 42 days, see how much material got oxidized. The top is an oxide. And when you say kappa phase, as I said in the earlier, I told they form some sort of precipitates also. and those are kappa phase that form not with iron aluminide, but with between nickel and copper. So that is what is happening. And a tremendous amount of oxide growth. So the earlier oxide, if we take into consideration and normalize it, maybe it may reduce the theory to this one. But still, I'm a believer that we are missing somewhere to look at the relationship between the surfaces. So in conclusion, what I want to do, the overall corrosion process is in copper, nickel, and aluminum is a diffusion control process. For iron, the process is depending on one species whose concentration is changing with time. That means a first order reaction. And as I said, the whole thing is coming in. In the fast corrosion region, copper and nickel follow the first order. Aluminum is diffusion control. Iron follows a second order. This is in the fast region. Rate of corrosion is iron is greater than aluminum, is greater than copper, greater than nickel. That means nickel is much more corrosion resistant than any of these things. The surprising is aluminum, but because it is associated with iron, it is the whole thing coming. So in the slow rate of reaction, it is showing some reverse reactions also. Complex oxides are forming and then redepositing it. So from the structural analysis following this one, copper oxide hydroxide appears to grow continuously, which is a common sense. I mean, if you take copper pipes or even brass pipes, you will see all the time the blue plaque forming. So it is a continuous, it will not stop. During the first 10 days, the reaction is very slow. And once it starts, in fact, it is not 10 days, it is actually 12, 13 days. The rate is forming increases significantly. Nickel and aluminum oxide or oxide hydroxides form passive layer. That's the reason why it is the slowest one. The first week rate of oxide hydroxide forming increases, and it appears that after nearly 3 weeks, aluminum oxide forms a passive layer. In fact, based on that one, we made a simulation curve. So that is the schematic representation. So it is happening. To start with T equal to 0.
Vegetarian.
It is T equal to 0, it is air oxide only. And T 1 to 5 days, you have different species. In fact, if you ask me what it is, I can't. Red, I know it is iron oxide or copper oxide. I mean, please, we just identify different colors. Please don't brag me on that one. So for first 1 to 5, some oxide is forming. Okay, it is a schematic. So we thought at T0, there is no air oxide, but it has a thin film. After 10 days or 12 days, the alloy surface is completely, the reaction is very aggressive and it forms inhomogeneous, not homogeneous formation. And after greater than 10 days, a continued buildup. And you can see the very, very loose, and in fact, the computer generated this picture. It shows a very loose porous structure. Unless there is a porosity, the liquid cannot reach the metal, and you don't see any corrosion product. So this is the open circuit, and then we wrote a report on that one. So with this one, I would like to thank you for giving me this opportunity to talk to you and about present our results. A different perspective results for the chemistry, people in the chemistry faculty on the corrosion. Although corrosion belongs to chemistry, it's no more in chemistry, it's in chemical engineering. With that one, I would like to thank you. And if you guys have any questions, the way we think, I mean, I have been in this country for more than 45 years. I left India in 74, and I have been here. So the way you guys think that I have an accent, and Indians talk, it's difficult for me to understand too. You guys talk very fast. So please, I can't hear first, and then you speak. So please speak loud and clearly so that I can tell. If not, send me an email or send me your question to Dr. Prabhakar Rao or Dr. Basweshwar Rao. They can send me back and I can answer it. Thank you very much.
So thank you very much, sir, for your wonderful talk. Any questions, maybe you can unmute yourself and you can ask slowly.
Sure. So you have to unmute so that
unmute one person and maybe you can speak slowly one by one.
Sir, it's a very good talk. I am Lakshmi Kumar from SRM University, Chennai. So can you hear me, sir?
Yes, sure.
Maybe I am not from this subject background, but I have a small doubt, but I don't know whether it is relevant or not. See, nowadays for making these aeroplanes, all these things, they are using that foam metals, right, which are highly corrosion resistant. That's what the emerging research is coming.
Yeah.
Can I have your comment on this?
Well, the reason is it depends on the application. See, when you say naval vehicles, they are supposed to be carrying a huge loads, and also they should sustain very high stresses because, I mean, when you are underwater, I mean, the sea is all, we call them pressure vessels, basically. We don't call subs pressure vessels. Whereas in the case of aeroplane structures, you don't have that sort of stress, external stress. But of course, and also the loads that carry is less. And the composite materials, in fact, almost all the things you are talking about, they are made of composite materials and intelligently processed. So they can carry much more heavier loads. Okay.
Thank you, sir.
Good morning, Dr. Rao. This is Yashodhara Rao, and I have a quick question. You had mentioned about stress corrosion cracking briefly in your presentation, and I wanted to kind of ask a question regarding the slow process rates that you were discussing when it came to the corrosion processes. Had you considered that when we consider stress corrosion cracking, we're looking at material, we're looking at environment, we're looking at the stressors, but when we look at environment, especially when in the naval application, had we considered the flow rate that we see, especially because of being exposed to seawater and being in constant movement, the subject to different types of flow rates that could occur, the oxide diffusion that can be applied?
Okay, your question is very interesting and important question. See, right now, all the tests, generally the chemists, what they do is a static test. That means there is no Reynolds number involved into that. As you said, the moment flow is there, you are in a different arena. And actually the flow expedites the process. That means if we have, in fact, that is, well, I shouldn't say that because I'm forbidden to talk about this nuclear work. The moment you have some sort of a vigorous application, so whatever is passivating oxide forms, it's immediately taken. That means every instant AI, it is creating a new active surface for corrosion. So it accelerates, and of course under stress it is much more. So that right now today's talk is more chemistry. Where they do static testing. I mean, are very, very low Reynolds numbers. Okay.
Thank you very much.
Yeah,
Any other questions?
In fact, I finished 15 minutes early because I like to entertain the questions. I mean, that's where it's a mutual. You will have the different approaches that comes into my mind too. What we missed or whether we can improve. So please don't hesitate and ask. There is nothing simple question or a difficult question or a silly question.
I'm Dr. Subbaya from Vignan University. Where this we can apply? Actually, in seawater, how much ammonia mixing, this type of applications we can get?
I know the answer, and you put me in a situation. The reality is why, see, some of the things, salient points we don't. In fact, the organizations here, they don't want us to talk. All the time they want to send, when we send people, they want to send managers, I mean, top management, because neither they have anything in their mind or the people with whom they are talking will have anything in mind. So the proprietary information is kept. See, when we have this 10%, 20%, 50%, it is the worst case. And what we are doing is, they told you in the beginning, the whole corrosion process is having, corrosion issue is coming because of the effluent that is coming out of the washing machines. So we calculate how much effluent come and what is the loss per year. So based on that one, we will do that. I mean, I am answering you a long-winded answer because I have to do justice to, I mean, as a scientist, I should answer you. And as an American national, I have to protect our naval. I mean, it's a proprietary. You understand?
I am also a retired scientist, but I worked on nickel hydroxide, nickel oxide, copper. This is synthesis of these materials only, but I don't have the experience of corrosion.
Well, in fact, the application for that one for naval vehicles is many. In fact, please make none of these. Okay, I have, and you guys saw I have about 300 papers, but it is only 20% or 25% of my work. 75% I have not done anything yet. I have not published. And that is the actually paradigm, what we face, where, in fact, I was telling to Dr. Basvesarao the same thing. If people work in industry, most of the work never comes out, except for flight. And in naval applications, I just showed the propulsion because it looks nice. But there are many, many things. Actually, I remember in one of the pumps, the closing valve will have actually a brass inlet-outlet flow. And that brass ball, you call whatever you call it as, it is at least 12 inches in diameter. This big ball, almost like a volleyball type of thing. So severe corrosion you can see. You are right, there are a lot of important things. And depending on the situation, in fact, we have done some testing, next time I can talk, on concentrated KOH to accelerate the corrosion, to make a prediction on what happens in 10 years' time. So the simulation calculations are there. Okay.
Thank you very much, sir, for a very good, impressive lecture.
Any other questions, sir?
On behalf of Andhra Pradesh Academy of Sciences, I really thank Dr. Appajosula Srinivasarao garu. Actually, this is a really international seminar, as we have participants from Korea, Malaysia, Japan, US and UK, and also all the states of India from Delhi. I see some participants from Delhi, Nagaland, and really it is useful, sir. I request, it is unfortunate due to COVID, we cannot make our programs physically and we are going virtually. So at least I request Prabhakar Rao to show the memento to all of us, which is made, which is to be delivered to Dr. Srinivasarao garu at least by post now.
Okay, sir.
Can you show me?
So the moment I will be showing myself and our HOD, Professor N. Srinivasarao garu.
I am highly thankful to you, sir. I am Professor N. Srinivasarao. I am the head of the Department of Science and Humanities, Vignan University. I am highly thankful to Professor Srinivasarao, sir, for his excellent talk. We all enjoyed for your inspiration talk. On behalf of Vignan University, we thank the management, our management, as well as particularly Professor Basavesarao, sir, and Andhra Pradesh Academy of Sciences for this opportunity. Thank you, sir. Thank you very much. Sir, Srinivasarao, sir, I met you. I don't know whether you are, I have doubt. In 1990, I met in Benares University. Have you met? At that time, you came to India?
Yes.
Yeah,
Yes.
then
Sir.
I met you, sir, at that time. At that time, I am a student in Benares University.
Okay.
At that time, I met you, sir, at that time. And now I am the head of the Department of Science and Humanities. Thank
Oh,
you
that's
for your,
great.
yeah, thank you very much, sir. I remember you, but it is you are looks like a young still, because you are photo and as well as by virtually you are young now. I compare both the things. Thank you very much, sir. Now just
Thank
you
you.
can see the memento what we are present. On
Okay,
behalf
sure.
of management.
That's great. That's great. I'm really honored to receive this award. And
Photo is there, sir. Photo is there, and Naidu sir photo.
okay.
And
So I hope you.
Sciences.
Yeah, sure. In fact, Dr. Basavesarao, well, for
So we are going
please,
to parcel to you, sir, this memento.
so, please forgive me when we use the word, we don't say garu. I mean, although it is at the heart, it automatically comes. So please send it by courier, as you said, and that would be great. And in fact, actually next year, we are thinking, hopefully there is no COVID, we are thinking to have our 50th MSc student get together in Tirupati. So if it is possible for you to arrange another lecture in Tirupati coinciding that, it would be great.
Yes, sir. We will arrange at SV University or Padmavati University, sir. We welcome.
I don't, yeah, it's left to you, because the reason is I am right now intending to attend that one. And in fact, actually my colleague, he reached much, he was at the Atomic Energy in India by name Dr. Ram Kumar. He is also, I saw him earlier in the attending my seminar. He is the guy who is the leading this thing.
Sir, our Honorable President, unfortunately, is held up at the hospital.
Okay.
He conveyed his regards and thanks to you, and he will speak to you personally.
Okay, sure. Well, as I said, next year, definitely. When
I could not make up his time.
Mm,
He will call you personally after some time to your number.
Okay.
Thank you, sir.
All right. Okay, it's my pleasure. Thank you very much. So anybody has any other questions, they can always send it to Dr. Basaveswara, and I will be glad to answer whatever. Okay. Okay, but I should
Thank you
thank,
very much, sir.
okay, I should thank Prabhakar Rao.
Thank you,
Dr.
sir.
Basaveswara.
Even though some mess up is there, little bit of password, I must really apologize for this mistake. Maybe
No, no,
finally we end up with without any disturbance of the talks or failure
No,
in other
that
things.
is, yeah, we are used to that one. It's not, it went very smooth. And so that's not a problem.
Thank you very much, sir. We are glad to have your talks.
Fine. So I will just stop share. That's
Yes,
what
sir.
Yes.
Thank you. Basaveswara garu malli maatladtanu nenu. I will talk to you later. Manchi namaskar.
I'm closing this talk. Thank you, sir.